This conference will now be recorded.
Welcome, everybody. My name is Dr. Mary Beth Neely. I'm the scientific coordinator for GEO AquaWatch, and it is our pleasure today to introduce the latest seminar speaker for GEO AquaWatch, Mr. Jorrit Scholze with Brockmann Consult. He will be speaking on the City Water Watch project. Just as a reminder to everybody to please mute your lines until the conclusion of the presentation today. You will be able to place your questions in the chat. I will moderate the Q&A session, or at the conclusion of the talk, you can unmute yourself at that point and ask your question directly of Jorrit Scholze. The co-authors on today's talk, along with Jorrit, are Dr. Kerstin Stelzer, Carole Lebreton, Werner Blohm, and Christian Moldaenke, also of Brockmann Consult. Mr. Scholze works mainly on Earth observation projects and services in inland waters, which are our favorite in GEO AquaWatch. He also works on projects like City Water Watch at Brockmann Consult. He primarily does algorithm development, process automation, and also visualizations from the perspective of users and for customers of Brockmann Consult. He earned his master's in science in applied geoinformatics from the University of Trier in Germany, but his master's work was actually on a project in the Netherlands. And he has also earned quite a lot of experience, professional experience, through internships in Australia and Germany. And we are pleased that Jorrit is with us today because he also exemplifies our GEO AquaWatch's commitment to to amplifying the voices of early career scientists. So take it away, Jorrit.
Thank you very much, Mary Beth. So, hey everyone, I'm Jorrit, and yeah, Mary Beth already said a few things about myself. I'm very happy to show you a few things of we were and are working on within our CIWAWA or City Water Watch project. And this project aims mainly to monitor urban waters by combining remote sensing and in situ measurements techniques with user requirements and user expectations. Yes, therefore we are a cooperation of 3 partners in this national project. The first one is ourselves, so Brockmann Consult. We are remote sensing experts and work with water quality analysis from space and data processing in general for remote sensing. Then we have BBE Moldaenke. It's a manufacturer of environmental technology, especially measuring instruments and software for water quality. And we have the Institut für Hygiene und Umwelt, that's the Institute for Hygiene and Environment from the user side, who are responsible for monitoring the water quality for water bodies in Hamburg. The things we wanted to show you, we divided in 4 different aspects today. So the first one is urban inland waters in general, so a little bit about the CIWAWA project and about the characteristics of urban waters in general. The second part is the algorithm development for remote sensing data, so what did we do there? For example, surface water objects, clouds over cities, so distinguish them, or we trained a new set for the C2RCC algorithms, the C2X-Complex. The third part is, or are the in situ measurements, which field measurement techniques are we using, and a spectrometer design. And at the fourth point, the product development. So we set up a concept for a combined product between remote sensing data and in situ measurements. And we develop various interfaces for the user to interact with this data. So within the CIWAWA project, we are focusing on water bodies in Hamburg, in Germany. They are often used and important environments for humans and animals as well. And not only within the inner city, but also with their surroundings. In Germany, we have two main water bodies. As you can see here, the Elbe, the river, it's the second largest river in Germany. And it has a high economic interest with its harbor. You can see at both at the lower pictures. So it's quite a big harbor. And with the Alster, that's the artificial lake here in the inner city. You can see pictures on the left, on the top and right left, which is often used for activities like sailing or rowing or tourism as well. So we have a lot of tourist ships on there. So water bodies in general are very important for not only the urban climate to improve it, but also for urban life in general. So what are we doing in CIWAWA and what are the components? You can see here a model of it. We have on the left side, we have the column for remote sensing. On the right side, we have the column for field measurement. And in the center column, we have the concept for product of these, which is built on a foundation of requirements from users, on methods, and on validation and the product design. And the roof is a combined product of those parts. But before starting to analyze waters, you have to consider that waters have some special characteristics and some special requirements, especially for the remote sensing part. I listed a few of them here. So we have objects on the water. We have adjacency effect, especially for bright buildings along the shoreline. Sometimes we have building shadows on the water surface if we have very high buildings. And we also had issues with clouds over cities, so distinguishing clouds and very bright roofs or areas in cities. And with this also a falsely classified cloud shadow in water bodies. Yeah, here are two pictures where you can see what we have to deal with objects on the water surface. So we have different kind of boats, like or large ships and smaller ships, which we need to flag. As a next step, I would like to say a few things about examples of these and how we are dealing with them. One which I already mentioned are the surface water objects. We implemented or we developed an additional spatial filter and we used the Laplace filter for this to identifying different objects and effects on the water surface, like boats, ships, fountains, wakes, or groins. You can see examples here on the images on the right. On the both left images are images from the Elbe, so from the river, where you can see like a lot of these small white pixels, which are often ships or boats. And on the lower picture, you can see even groins at the shore. And on the right side, you can see the Alster, where you can see if you have a very nice summer day, there are a lot of sailing boats on the river, which we need to mask out and we do not want to consider for the water quality analysis. And therefore we use a filtering on the Sentinel-2 images on the 10-meter resolution. And this is a 5x5 filtering. And if we apply it, you can see the results now in red. So these are the pixels we mask out. and nearly every pixel which is influenced by these water surface objects is masked. Especially for the Ulster, you can see that there's a lot of pixels where we are influenced by boats. Another issue which I mentioned was the clouds over cities. So to separate clouds from bright surfaces, we use the parallax effect, and we calculate the cloud displacement index which makes use of the near-infrared parallax effect. This is by Franz and Haas. And we use this CDI and implemented it into EDIPIX, which we use for pixel identification for Sentinel-2. And on the right, you can see the workflow of the CDI. So we use the ratio between the infrared bands and calculate a spatial 7x7 standard deviation filter, and then calculate the CDI. Here's an example on how this looks. So on the left side, or in both images, you see the Sydney area. On the left side, you see the older version of the EDIPIX, where we have yellow pixels, which are identified as clouds, and red pixels are the cloud buffer around it. And on the right side, you can see the new version, where you can see that we eliminated a lot of these false classified cloud images and reduced the error. Here's another example for the Hamburg area. So again, on the left side is the older version, where you can see yellow areas as clouds and red as cloud buffer. And especially here in the harbor parts where we have large bright roofs, so they are often classified as clouds. And on the water surfaces, you can see also blue pixels. So they are cloud shadows, so falsely identified cloud shadows, because the cloud shadow is dependent on the cloud mask itself. So if we have false identified clouds in the city, we also, or the algorithm thinks that the water surface is the shadow because it's the dark area. And on the right side, you can see the improved version, where we eliminated most of the false classified pixels, and you can see that the false classified cloud shadow on the water surface is eliminated. That are examples for cloud masking, or for masking in general, or pixel identification. Another part we worked on in the project is on the algorithm development and for water quality assessment. And therefore, the detection of Cyanobacteria is also a big part. And if you can read German, here's the headline of a news article from Der Spiegel, where it says that the swimming part of the Ironman in Hamburg was canceled due to high Cyanobacteria blooms. And this decision was made based on the in situ measurement of Cyanobacteria blooms. And here you can see the time series of this chlorophyll A concentration, which is based on in situ measurements. So in blue, you can see the chlorophyll concentration in total, and in red is the chlorophyll A concentration for the Cyanobacteria. And you can see that there are two main blooms in the year 2018. So in August or end of July, beginning of August, where the Ironman in Hamburg was planned. And then the swimming part was canceled. And another part, or another Cyanobacteria bloom in September 2018. Looking at the days where the Ironman was canceled, so end of July to the beginning of August, you can see also that there were two main blooms happening. So it was good that the Ironman was canceled there. And from the part of the remote sensing, we developed a detection algorithm for these Cyanobacteria. And we have, in this time period, 3 images to look at. And here you can see the Ulster again, where the swimming part should have taken place for the Ironman. And first image is on the 24th of July, so end of July, where you can already see that in most parts of the lake, the risk also from the remote sensing part was medium to high. And if we go 3 days ahead, then you can see that the risk for cyanobacteria is still medium to high, but this time only in parts of the lake, not in the whole lake. And if we go even a few days further, you can see that in most part of the lakes, the risk is now low, but we have a very nice spatial pattern where we see that the risk is even very high here in these parts. So this is an example where you can benefit from this combination of in situ measurements and remote sensing data. From the in situ measurements, we have this high temporal data set, and from the remote sensing part, we can see the spatial pattern of the cyanobacteria and make use of this. How did we detect the cyanobacteria with Sentinel-2? Therefore, we set up a random forest approach where we combine two models together. And the input for these models are based on bottom of Rayleigh reflectance. And with this model, we determine a pixel-wise low, medium, or high risk for cyanobacteria. For now, more tests are still needed for rivers and very high biomass blooms, but we're still working on this. Another part for the algorithm development for water quality assessment is that we trained a new set of nets, and we named it C2X-Complex Nets. So these are new sets of neural nets for the C2RCC for Sentinel-2. And there we characterized the bio-optical model based on in situ measurements from inland waters. So we updated and extended the bio-optical model for our training data set so that the extension of the ranges are now fitting for inland waters. And we updated the relationship for the bio-optical models between the parameters. For example, here you can see that now on the x-axis is the Secchi depth, and on the y-axis the Secchi depth, and on the x-axis is the chlorophyll concentration. And this is different for inland waters. So we used this kinds of relationships. So what does it mean? So how do the results look like? In Hamburg, we have 3 permanent measurement stations. You can see it here at the map for Hamburg. That's Seemannshöft and Bunthaus. That's 2 measurement stations in the Elbe, in the river, and 1 at Lumbertsbrücke. That's at the Alster, at the lake. And here you can see for each station a scatter plot of the chlorophyll A concentration. And we have on the y-axis the remote sensing chlorophyll A concentration, and on the x-axis the in situ chlorophyll A concentration. Here, these scatter plots are now based on the first set of nets, so the C2RCC normal nets. And you can see that they underestimate the concentration quite a lot, because these nets are trained for ocean and ocean applications. So they are more used for very clear water. Then we have a set for C2X nets. That is where you can see that in all stations we still underestimate the concentration, but it already improved. But these nets are also mainly used for coastal applications. So for inland application, we now trained the C2X-Complex Nets. And you can see that for all stations, this improved, and we have now quite nicely relationships between them. And here you can also, or you need to consider that these 3 stations are very different. For example, Seemannshöft has the lowest concentration and is very influenced by suspended matter. Lumbertsbrücke has medium to high concentrations, and Bunthaus, this is the southern station here, has very high concentrations up to 200 microgram per liter. So summing up the part of the remote sensing, we set up a near real-time processing for the Sentinel-2 images, where we apply the object filter on 10-meter resolution and then use the eDepix on 20 meters with the cloud over city approach, and then calculate the atmospheric correction and the water quality parameters with the C2X-Complex Nets, and then derive the Sentinel-2 Level 2 images. A big part of the CIWAWA project is as well the validation and visualization of the data, where we often look at time series and maps. But for the validation, we also need in situ data, where we have different sources. As I already mentioned, we have these permanent in situ stations. Then in Hamburg, we have regularly harbor cruises, and we have scheduled in situ cruises in different parts of water bodies in Hamburg. On these in situ measurements, I would like now to focus and say a few things about them. Because within the project, we use different devices, which are all manufactured by BBL Moldaenke, our partner in this project. In the permanent in situ measuring station, the algae online analyzer is used for online measurements of water quality. You can see the setup here in the image. Then we have two devices, the fluoroprobe, you can see on this image here, which is an instrument for the analysis of chlorophyll with algae class determination. And we have the Fluorostar, which is in development or ready to use at the moment, where we have the method of adaptation to the dark implemented, so it reduces the influence from sunlight on the fluorescence effect. So it tries to eliminate this error during the measurement in the field. So these both measurement devices are used directly in the field if you make like measurements campaigns. So how does it look if you combine these two kinds of measurements? Therefore, we looked a lot into the time series within the CIWAWA project. And here you can see again a time series of the chlorophyll A concentration, where the blue part is the in situ measurements. So it's a permanent measurement station, again here Seemannshöft in the Elbe. And the red part are the calculated chlorophyll A concentration from the Sentinel-2 with the C2RCC algorithm. And we can see that it looks quite nice and fits nearly every year, except for 2016, where we overestimate the values a little bit. But if you focus to 1 year, you can nicely see that the remote sensing measurements are quite in line with the in situ measurements for the whole year. Here's another example for the station Bunthaus, where we have again the time series from 2016 to 2021. So it's the station also again in the Elbe, where we have very high concentrations, so up to 300, measured by the in situ measurement. And if we focus again on 1 year, you can nicely see that both measurement techniques have increased. Here in the spring bloom, then we have a nearly constantly high concentration for the summer bloom, and then it decreases towards the winter. Another special thing or another special device which was developed during the CIWAWA project is a spectrometer. This spectrometer was also designed by BBL Moldaenke, and here you can see a model of it. So you can see that 4 spectrometers were used for this device. We have the spectrometer 1 for measuring ED, then the spectrometer 2 for measuring LS, a spectrometer 3 for measuring LT, and we have another spectrometer here in this black box to measure the exact water leaving radiance. So this device is set up on a platform which has also a rotary plate. So this moves according to the sun. So they put a little thought in this and also measure simultaneously the wave movement and also the wind to filter out measurements afterwards. On the right side, you can see the spectrometer on this measuring platform. So the spectrometer was just set up a few months ago. So the first measurements was just taken. And the second one, so the spectrometer which measures directly under the water surface, is set up here. As I said, they just started to measure, and they still have some uninvited guests, as this is, for example, the seagull. Although they set up some protection like these spikes, the seagull seemed to very like this spot. And as you can see, the foot is directly on one of the spectrometers. So they're still facing some issues, which is yeah, quite funny. So what is the plan to do with the data? As I already said, they just started to measure some data. Here you can see an example of the different spectra they are measured. And if you look, for example, on the one water-leaving spectra, it looks quite nice. So the plan is for these spectra to have a pre-processing step and then use artificial neural networks with a training data set of in situ measurements, which are simultaneously taken to the spectrometer data, and then to derive out of these artificial neural nets an algae concentration. So summing up the first part of our CIWAWA project is that we looked at the first column, the remote sensing column, and which algorithm development we did based on also user requirements and user knowledge, and the field measurement I just talked about. We now want to build the center column and the roof as a product, and therefore we discussed advantages of a combined product, and we also set up a selection of interfaces based on user knowledge and user requirement for the user, which can be used. Therefore, we set up a workflow for a user product. And there on the left side, we have us as our partners, so BC and BWE Moldaenke, and the Institute for Hygiene und Umwelt as a user. We at BC are responsible for the remote sensing data, especially for the water quality data and some external data if they are present. BWE Moldaenke, of course, manufactures the devices, and the user then uses these devices for example for permanent in situ stations or harbor cruises in this case, or just measurement campaigns. The remote sensing data is then stored in data cubes. So we are here in the X-cube world, where we do take data cubes out of these remote sensing data and store vector data in the GeoDB. There, for example, these continuous or permanent measurements from in situ measuring stations can directly go into the GeoDB and can be managed there. For the interface for the users, which I already talked about a little bit, we set up 3 different interfaces, which all use the data cube as the foundation. The first one is the viewer for raster data. So that's the first level of as an interface where the user can just analyze or just visualize the data and look at some time series. And for the next slides, I would like now to just say a few more things to each of these interfaces. As already mentioned, the viewer is one of the interfaces for the users. As you can see here, it's a web-based viewer. And we have here, for example, now the Hamburg data cube, where we have different variables. And we just looked at some RGB images. And then you can just look at the data and visualize it. So not just only RGBs, but also here the chlorophyll concentration, for example, over time. And you can also analyze regions of interest. We are now looking here at Außenmühleteich, that's a small lake in Hamburg. And let's say we just want to have a look at this Außenmühleteich a little bit closer. So we set up a polygon, you can see here in orange, and we want to know, okay, how is the time, or how's the chlorophyll concentration over time in this area? And if we set it up, then you can here see on the right, over the full time period of Sentinel-2, how the chlorophyll concentration is developing. And then we say, okay, we just want to look at 2018. And then you can see all the data points for each day and how it just develops over time. So here we have a summer bloom, and then it decreases, and then a small autumn bloom again. So that's the first step of interface for the user, just to visualize the data. So looking at raster data and looking at time series. And the next step, if the user also wants to interact with the data and work with the data itself, we set up, or we work with Jupyter Notebooks. So Jupyter Notebook is a web-based environment that allows you to write, document, and demonstrate your code. And it's often used for data analysis and visualization. We use these notebooks in the CIWAWA project for time series extraction and analysis, for spatial statistics, for the data preparation for web map surfaces, for example. And you have also the possibilities to run models or for classifications or regressions. So for the next step, I would like to show you a few quick examples of a Jupyter Notebook we set up. I hope you can see it. So here you can see it's a Jupyter Notebook based on Python, where we work with the data cube, the Hamburg data cube itself. So here we just first load some dependencies and some packages, and then this is just to open the cube. So we have this Hamburg data cube where we have all our remote sensing data included, and we open it with the Xcube package. And then you can see that the data cube looks like this. So we have lat long, and we have a lot of time dates, and we have our data variables. So we have plus filter, we have the chlorophyll concentration, the suspended matter, the Secchi depths, and some TOR, top of atmosphere bands. And the first part is on how to retrieve here time series. So for Hamburg, we have our 3 stations. We just, for example, choose here Bunthaus. Then we can choose, we say, okay, we want to look at our chlorophyll A concentration. Then we set up the coordinates. For this, we already choose Bunthaus. And then we extract here a 3 by 3 pixel area for this measuring station. And we exclude here in this part outliers with the Z-score, and connect this to in situ measurements. And if we plot it, then it looks like this. So we have a nice time series plot with the in situ data in blue, and again in red, the remote sensing data. So we combined both measurements technique together within the Jupyter Notebook. What we also can do is then just look at a time period we are interested in. For example, here it's now 2018. And it's again the Bunthaus station, and we then plot again and see, okay, we have a nice time series again, and now we can analyze how these 2 measurement techniques behave to one another. Another part would be to use Jupyter Notebooks within our spatial analysis. Here we set up an interactive map. So this part of the code just sets up this interactive map where you can draw, where you can just set up your area of interest. So we say, okay, we want to look at this part of the Elbe more closely. So we set up our area of interest. Then with this part, we just clip our data cube with which we already looked at to this part of the so our area of interest. And just with this line of code, we say, okay, we want a monthly mean. over the year of 2020. So we subset our data cube to this year, to 2020, and group it by the month. So if we do this and look at the cube again, then you see, okay, we have still our lat long, so that's our area of interest. And now we don't have the single time dates anymore, but we have our months. So we have January to December, and we have still all our data variables. So that's very easy to access. And if we then just want to plot them, it takes a little bit of time. Then you can see, okay, for every month, we can now look at our monthly mean for the area of interest we have. So in January and February, we don't have any data, but then for March, April, we can see that the chlorophyll, in this case, we're looking at here, is rising, and in May as well, and then it decreases again for June, July, August, and September. And in the last 3 months, we don't really have any data because Hamburg is very cloudy in these months. So with this demonstration, I just wanted to show how easy it is to access the data cube with Jupyter notebooks and combine it with in situ data. And here the user can do all kinds of things. So if you want to investigate the spatial patterns more closely, and of course he can also combine it with various parameters. So you can combine Secchi dips, for example, with chlorophyll or different ones, and you can combine it also with measurement campaigns. So yeah, that's what the part of the Jupyter notebook. So now we have the first level for the viewer just to view and the raster data and analyze it. The Jupyter notebook to work really with the data. And for Hamburg, we have another tailored user interface. That's where we set up services, so web map service and web feature services. Because in Hamburg, we have regularly these harbor cruises. Here you can see the Elbe again, where the harbor cruises drives along these segments with the boat and makes measurements a few times in 1 year. And remote sensing data could here be a very nice additional data source for information. And therefore, we prepared the remote sensing data according to the data format they are using. So here, for example, we have our raster data for a closed day of the same of this harbor cruise, and then for each section we also calculate the mean and have a similar data format as the in situ measurements. So what do we do with it? Oh, that's wrong, sorry. So what we do, we also calculate the web map service out of these raster data, and then we implemented it to the GEO portal in Hamburg. And then you can look at the harbor cruises for the in situ measurements, but also on the harbor cruises based on remote sensing data. Yes, so now I'm coming already to my last slide. So summing up what we did in CIWAWA, I talked a little bit about the algorithm development. So not only for urban waters, so what we did for masking, so pixel identification, but also for algorithm development for water quality assessment. And I talked a little bit about the development of interfaces, which are adapted to the user, so for user knowledge and for user requirements, and the integration of these different data formats. And within CIWAWA, we learned that the combination of remote sensing and in situ measurement in inland water shows that it gives very nice additional information sources. So especially the combination of temporal and spatial information. And what we also learned, that there's a possibility to optimize the monitoring of urban waters. For example, if you have this spatial information from the remote sensing side, you can then say, okay, here's a very nice spatial pattern in this part of the water bodies. Let's set up a measuring station with in situ here and look what's happening over time. Yeah, and therefore I would like to thank you for listening. And yeah, if you have questions, just let me know.
Great, thank you very much for your talk, Jorrit. It was excellent. If anybody has any questions, they can drop them in the chat, or you may unmute now and ask Jorrit your question directly. While people are finding their mute buttons, I will just mention that that your talk is quite opportunistic in that I believe it was 2 days ago was the at COP26, the focus was on cities, and certainly water quality is directly related to climate impacts, and that's urban areas are also an emerging focus of the group on Earth observations, GEO, as well. So I just wondered if you could comment on perhaps the scalability of the CIWAWA project to other areas globally, or even just within Europe.
Yeah, sure. Actually, this was also part of the project. So we already did this a little bit. We looked at different cities where we could where we had similar in situ measurements, but this was also already just German cities and just smaller cities, but the results were very similar. So we had quite a nice correspondence between in situ measurements and remote sensing data. We had, yeah, for example, a measuring station in Potsdam, that's near Berlin, where we had a look at. And yeah, to do it even global or even in Europe, that would be very nice. But therefore, we first would need to collect some in situ data and to see how this works.
It is a great example of the combination of Earth observation and in situ data, even in urban environments, which often do not per se suffer from a lack of measurement
Yeah.
because of. But you know, you showed, especially with the high resolution Sentinel-2 data, what you were able to see on the lake affecting the Ironman competition, and how the in situ measurement might show everything's clear, but the satellite data indicates that it is not, or vice versa.
Yeah, that's a very nice example. Yeah.
Does
yeah,
anybody
we've seen
else?
this in.
Oh, go ahead.
Yeah, we've seen this in different lakes, but it would be nice to have more urban examples, as you said. So that's a thing we could have a look at if we find more examples of these in other cities.
Let me tell you, the United States is rife with urban impacted lakes. Come over here. Anybody in the audience have any questions of Jorrit or anyone else on the team? I do have a couple more. I'll just go ahead and ask.
Okay.
Anybody? I don't want to feel like I'm interrogating you. I especially liked the fact that you said through your Jupyter notebooks, you enabled your customer in one case to customize the product, and I'm guessing take take some sort of ownership in producing the product and in branding it. And I wonder if you or maybe one of your co-authors who might be on the call today could elaborate on how that helped, either with the communication of the information as a trusted source to the community, or maybe in getting the project funded. That, you know, it came with the caveat that it had to be branded with them, or you know, and have some sort of ownership element by them.
Okay, maybe.
Is that true? Maybe I misunderstood that, you know, the utility of the Jupyter notebooks, so that they could produce it themselves.
Yeah, so if you have like some sort of service, or if you can even like produce a data cube yourself if you have the data, because the XCube package we are working with is a free package, a free Python package. So if you have the data, you can do your own data cube, and then you can work with them in Jupyter Notebooks. But if you, of course, want more features like the viewer, then it's more of a service.
Right.
Yeah, so the processing, the full machine that is behind this is, I mean, you can do all by your own because many elements are open source, but having this all in place now is quite a good value. And so this is what we also provide as services. So if there are people that are interested. But of course, many of our, as you might know, many of our software and elements, as the XCube and the C2R are open source, and EDPix as well. So the single elements are there and also accessible. But having this machine and this combination of everything, yeah, it's quite valuable, I would say.
Great. Any other questions for Jorrit or anybody else on the team? Well, just a reminder that the presentation today was recorded. It will be up on our website within the next couple of days. And congratulations on your work, Jorrit and the rest of the team from Brockmann Consult and Moldaenke. And we certainly wish everybody to have a great day. Thank you very much for coming, and thank you especially for your presentation, Jorrit. It was wonderful.
Thank you very much, and thank you for having me.
Thank you.
Thanks a lot.
Thank you.
Bye, everybody.
Bye-bye.
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 Bye-bye.